Hi, in this recording we're going to be looking at tutorial 4, question 3, which is on the data path and control of the MIPS processor for three separate instructions. Okay, so let's look at the first instruction. The first instruction is a load word instruction. So a load word instruction loads data from this memory location into this register 24. So the first thing we need to do is of course translate this instruction into its binary representation through the MIPS encoding technique that we have already learned. So this is the full translation, and putting that here, okay, in this area here, you can see that we have the opcode RS, RT, and RD. So in this case, we have the opcode here. The RS is 15, okay, RT is 24, okay, and the immediate value is 0. Okay, once this 32-bit instruction is supplied to the MIPS processor, you can see that, for example, here this wire is connected directly, same as this wire. So number 15 or value 15 is directly supplied to read register 1, and value 24 is directly supplied to read register 2, which means that from the register file, the data from register 15, okay, and the data from register 24 would be automatically available at the RD1 and RD2 of the registers. Okay, now what is interesting here is we only need to read from register 15, okay, because the instruction, the lower instruction, is reading from register 15 and adding it to the immediate value to obtain the final address. Okay, so we are not actually going to read from register 24, but still, since it is already hardwired, okay, these bits are hardwired to RR2, it means that the register file will still be activated to provide the contents of register 24 at the RD2 bits. Okay, so you can see that in these slides, those in red means the data is actually used, whereas those in blue means it is not being used. Okay, but it is still present there because of the way the processor is already wired up. Okay, now the next thing we need to look at is the control signal. The register destination is having a value of 0. Okay, and this control bits, register destination, register write, ALU source, and so on, are generated from the control block here. Okay, so you have studied the control block and you know that inside the control block there is a bunch of combinational logic circuits that will use the opcode to generate the appropriate control signals for the various stages in the processor. So for this load word instruction, the register destination would be 0, which means that the bits corresponding to the RT location are the ones that will effectively get channeled through to be the write register. Okay, so the write register would also be having a value of 24. Okay, then what happens? The next stage is your ALU. Okay, so we can see that. Okay, so let me just change the color here. Okay, so we can see that the RD1 is directly connected to the operand 1 of the ALU, which means that that is already available at the first operand. How about the second operand? Okay, so the second operand has to go through this multiplexer. Okay, and since this is a load word instruction with immediate value, the ALU source, okay, must be set to 1. Okay, that means the immediate value here, okay, will get sign extended, come here, and then go as the second operand. Okay, so that is your ALU source here. Okay, next, what we just now did not look at is the register write. Okay, so the register write here is also set to 1 by the control block, because this instruction load word will eventually take data from the memory and update it to the register. So we need to perform a register write at the end of this instruction. So the register write is set to 1. Okay, now what happens next? Okay, so we have seen that the ALU, the first operand is from data from register 15. The second operand would be the immediate value sign extended. So the immediate value in this case is 0. So when I sign extend it, it also becomes 0 over here. Now, the next stage is your memory access. So to perform a memory access, this ALU will provide a result here. And this result here is actually the data in register 15 add with the immediate value. So this add operation, how does the ALU know it's supposed to do an add operation? That is through the ALU control unit here. And this ALU control unit takes in inputs from both the main control unit as well as the function field. Okay, using these two inputs, again the ALU control has a bunch of combination logic circuits which will then decide how to toggle the ALU control bits to tell the ALU to do the correct operation based on the instruction it is currently executing. So the ALU control would tell the ALU block that is supposed to do a add operation. Okay, so this add operation would provide the effective address to the data memory. Okay, then what happens? The data memory has two control signals, memory write and memory read. So in this case, a load word instruction, okay, is supposed to read from the memory and write to the register. So it would mean that the memory read has supposed to be a 1 and memory write is supposed to be a 0. Okay, so memory write is 0 and memory read is 1 because we are reading from the memory and transferring back to the register. Okay, another thing that we will notice here is the write data here is directly connected to RD2 here. Okay, so previously we saw the RD2 is mapped to RR2 and RR2 has a value of 24. So the value in register 24 is directly mapped to the write data pins of the data memory. Okay, but we do not need to be concerned about this because your memory write is a 0. So if memory write is a 0, even though I provide some data to the write pins, nothing will actually get written to the memory. Okay, so we do not need to be worried about some data being present at the write data pins of the memory. Okay, so once we provide the address and the memory read is set to 1, the data that we want would be available here. Okay, so this is the data that we want, the data from the memory that we want to channel back to the register file. So in order for that to happen, the mem to register has to be a 1. Okay, so the mem to register, if you recall, is the only multiplexer where the top pin is a 1 and bottom pin is a 0. Okay, so the easy way to remember is mem to register means from memory back to the register. Okay, so when the mem to register is a 1, the data that is coming out of data memory will be channeled through the multiplexer and it will go back here, okay, all the way to the write data. Okay, and from the instruction, okay, and the register destination multiplexer, we already know that the write register is 24 and now we have the write data, so we can complete the instruction by writing the correct data to the register that is specified. Okay, so the write data is the memory location specified by the address that is obtained by adding the content in register 15 with immediate value of 0. Okay, so that basically shows you the whole flow of the instruction execution. Okay, just a few things to take note of here. Okay, so how about the branch? So this is not a branch instruction, so branch is 0. And ALU op and ALU control, you can refer back to your truth table that you have, okay, on the control block unit. And what I want to highlight here is the blocks that execute and whose operations are actually not being used. Okay, so if you notice this immediate 16 bits here, we sign, extend and send it to the multiplexer here, but at the same time it is also connected all the way up here to the left shift, and it goes to the adder. And here also there's a PC plus 4 that goes to the adder and goes to this multiplexer. If you recall, this section here, okay, this whole section here is actually used for the branch address calculation. And even though it is not a branch instruction, all these wires are hardwired. Okay, all these connections are hardwired, which means that regardless of the instruction I'm executing, I will still go ahead and do all this to prepare an address, even though it is not actually an address, because the instruction here is a load word instruction, so I'm not actually doing a branch. Okay, so this is what I want to highlight, that in the processor, multiple things can happen in parallel. Okay, but the control unit together with the multiplexers will be able to channel the correct data to each stage step by step to ensure that the operation happens according to the instruction. Okay, so there will be a lot of other things that also happen, and the reason why we do it is we want to prepare the data as much as possible in advance. Okay, so that the moment the control signal comes in, we can quickly channel the data to the next stage. Okay, instead of waiting for a control for some control signal and then deciding what to do. Okay, so that is why some of these components in the processor are actually hardwired to execute regardless of the instruction that you are performing. Okay, so that is the first instruction that we looked at, and of course after this instruction, your next PC value will be the current PC value plus 4. Okay, so this is the whole load word instruction. Now let's look at the next instruction, which is the BEQ. Okay, so a BEQ is basically going to compare. Okay, so this is your RS, this is your RT, and you're going to compare this and then jump to 12 lines away if your value register 1 is equal to value register 3. So this 12 means I will jump to PC plus 4 plus 12 times 4. Okay, so PC plus 4 is will be the PC location once this instruction is being executed by the processor, and 12 is, again, think of 12 as the number of lines of code. Okay, so each line of code is 4 bytes. Every instruction is 4 bytes, so 12 means 12 times 4 bytes away. Okay, now so the first step, again, like I said, is this, which is to translate it into its MIPS encoding equivalent in terms of binary. And once you have that, you have your RS, RT, and your offset. Okay, and as we have seen before, your RS here has a value of 1, and your RT here has a value of 3, and these are directly connected to RR1 and RR2. Correct? So the data in RD1, RD2 will be the data in register 1 and data in register 3. Okay, so that part we have seen before, and as before, we saw that this will also get connected here, and the multiplexer also has another input 1 here for the register destination, and this register destination, the second input, is mapped to bits 15 to 11. Okay, so in this case, this immediate value 12 occupies bits from 15 all the way to 0. Okay, and since the value is 12, it only occupies the last few bits here, and the upper bits are all 0. Okay, so the bits that correspond to the locations 15 to 11 have a value of 0 inside. So there is either a value of 3 here at the multiplexer input 0, or value of 0 at the multiplexer input 1. Okay, so this is what we can observe in the first stage of the processor here. So RR1 is 1, RR2 is 3. Okay, now for a BEQ instruction, for a branch instruction, there is no updating of register at the end of the instruction, and there is also no memory access. Okay, so since there is no updating of register in the memory in this instruction, it means that this register destination can hold any value, doesn't matter, because this register write would be 0. Okay, if register write is 0, it does not matter what value I put here in the WD, okay, or what value I put here in the WR, because register write is 0. So because of that, your register destination actually can hold a X, that means any value, it doesn't matter. Okay, so the write register could either be value 3 or value 0. Okay, so it doesn't matter. Now the next stage is your ALU. So let me change the color here a bit. Okay, so for the ALU, okay, we can see that 1 is mapped directly to operand 1, and 3 has to go through this ALU and then this multiplexer, and then get channeled to the operand 2. So for this, my ALU source must be 0. Okay, so ALU source must be 0, and just now I already mentioned that the register write must be 0. Okay, so just to recap what I said in the earlier slide, all these control signals are determined by your control unit here, okay, which will use a combination logic circuit, and using the opcode decide how to set or clear the various multiplexers, okay, in our processor. Okay, so once I have register 1 data and register 3 data applied to the ALU, the BEQ operation effectively does a subtraction. Okay, operand data in operand 1 subtract data in operand 2. Okay, so what will come out of here is actually register 1 data subtract register 3 data. Okay, and this will actually be presented as a address to the data memory. Now, since we know that a BEQ instruction does not involve any memory access, the control unit will automatically set memory read to 0 as well as memory write to 0. Okay, so even though I provide an address, it still does not matter because I'm not going to do any reading or writing. Okay, in this case, this is a branch instruction, so the branch bit here will be set to a 1. Okay, that means this AND gate 1 input here would be set to a 1. Okay, the ALU op and ALU control, I'll leave it to you to look back at your truth table. And what would I provide as data memory address? Like I said, the address would be value in 1 minus value in 3. Okay, so of course, just to reiterate again, this is not any valid address that is related to the question. Okay, to the instruction. The instruction is a BEQ. Okay, but since it is already hardwired over here, it will present itself as an address. Okay, but we do not need to be concerned about it because memread and memwrite are both set to 0. Similarly, write data is also hardwired to RD2. Okay, so the content in register 3 would also come to write data, but we also do not need to be concerned about that. Okay, and since register write is 0, whatever comes back here, okay, comes back here to the WD pin, again has no significance to us because the register write is 0. Okay, so that means the mem to register can actually be a X. Okay, so it is a X because whatever comes back here will have no impact because my register write is already set to 0, which means I will not update any of the registers. Okay, so the write data that actually comes back here could be two things. Either it is the data that is in the address location of 1 minus 3, or it could be some the data that comes back could be either the value 1 minus 3, which is connected to the ALU result here, or it could be some random data which is in the location of memory in address location of 1 minus 3. Okay, so this is just a memory location whose value would be the address of the data in 1 minus data in 3. Okay, so this could be some random value which you do not know, or it could be the actual value of the data in register 1 minus data in register 3, which is connected to here. Okay, So it could be either one, but it again does not matter to us because in a BEQ instruction, we are not going to write back to the register file. Okay. So for the BEQ, instruction, okay, so it is important to note that we need to take the immediate value here, do the sign extension, alright, and this value will come up here to do the left shift by 2, which is actually the multiply by 4, and then add with the PC plus 4, which is here. So this is your PC plus 4, and that gives me the new address. Okay, and this is the original address if the branch is not taken. Okay, so if the branch is taken, it's PC plus 4 plus 12 multiplied by 4, or if the branch is not taken, it's just PC plus 4. Okay, so that is the next PC value over here. Okay, so I hope this is clear. Okay, and now let's look at the last instruction, which is a subtract instruction. Okay, so for this subtract instruction, okay, we're going to do the same thing. So this is a R type instruction. So this is your RS, RT, and this is your RD. Okay, once we do the encoding over here, we can translate everything to the bits over here. And now we can see that RS is holding a value of 20, RT is holding a value of 5, and RD is holding a value of 25. Okay, and so my read register RD1 would be the content in register 20, and RD2 would be the content in register 5. Okay, and this register 5 is also mapped to here, and it's also mapped to, and 25 is mapped to input 1 of the multiplexer. Okay, so let's look at what we have now. We have data from R1 is 20, R2 is 5. Okay, and for this R type instruction, your register destination is specified by the RD bits location. So RD register destination must be set to a 1. So this is what we want. Okay, so your register destination will be set to a 1. And your write register would be register 25. Okay, so that part we can establish based on the R type instruction. Now, once we have this, the next step is your ALU. Okay, so for the ALU, okay, so the register 20 data comes as operand 1, and we want the register 5 data to come as operand 2. Okay, so ALU source must be set to 0. Okay, and for this R type instruction, the data is always returned back to the register, so the register write must also be set to a 1. Okay, so that is what we have here. Register write is 1, ALU source is 0. Okay, so with that, your second operand is 5. Okay, so the data in register 20 and data in register 5. Okay, so this subtract instruction will generate ALU result, which is content of 20 minus content of 5. Right? Content of register 20 minus content of register 5. And this will present itself as an address. Okay, but again, looking back, this is an R type instruction, which means there is no memory access. Okay, so even though it is presented to the address, this is not a memory access instruction, which means that your memory will be 0 and your memwrite will also be 0. Okay, similarly, the data in register 5 will be presented here as the write data, but we do not need to be concerned about this because it is not a memory access instruction, so memory read and memory write are both 0. Okay, and the next thing is your mem to register. Now, this mem to register has two inputs. One is from the memory and one is from the ALU output. Okay, so let's look at that. Okay, so from the ALU output, I get this data, and this is the data that I want because this is actually the result. This is actually the content of 20 minus the content of 5. Okay, which is what the instruction is supposed to be doing. RS minus RT go into RD. So this is the data that I want to go back into my destination register. So I want this to be channeled back, okay, to my write data over here. So mem to register must be a 0. Okay, and the write data is the result of the ALU operation. So the branch is a 0. Since we're not doing a branch, ALU op, ALU control, you can refer back to your truth table. Okay, and the next PC value will be the PC plus 4. Okay, so if you look at this operation, again, this does not involve the memory. And as before, if you look back at the unused portions of the processor hardware, for example here, I will still do a sign extension and present an option here, but we're not going to use this. Okay, and similarly, I'll also do a left shift by 2 and prepare a branch address, even though it is not a branch instruction. Okay, so there are parts of the processor that will still execute and provide some data on standby, even though it may not actually be used in that particular instruction. Okay, so these are some of the things that we need to take note of. Okay, so these 3 instructions basically give you a good idea, okay, on the various types of instructions that the processor can execute and how data will flow, okay, for these different type of instructions. So we first look at a load word instruction, the memory access, a branch instruction, followed by a subtraction instruction. Okay, so I hope with this video you get a clear idea on the whole sequence of operations. In the next video, I will be explaining the timing analysis, okay, on how do we analyze the data flow timing, okay, for different type of instructions. Okay, so look out for that. Thank you.